SwayamPrabha. Digital India. Educated India.
Session here, and at this stage here we have Wednesday the 15th. We have 3 lessons about the thermal management and measurement techniques, and now we have 1 hour about heat pipes. So we have just decided with Arvin that tomorrow, instead of 2 hours, I can give 3 hours, and then so on Friday we are completely free. I will be in campus, so if you want to contact me, please, I can give you my email address, and you can write, and then we can meet. If you have extra questions or something to discuss with me, we can do this on Friday morning, okay? Because this indeed was the time where I was, let's say, available for this course. Okay, so tomorrow we are going to speak about the interfacial phenomena, so I will introduce the surface tension, and in fact we have 2 hours, now will be 4.3, of course, because I changed completely, and it's about CFD modeling. Okay, so I will give you a panoramic view about the different techniques that are used in multi-phase flows. Of course, again, in 2 hours, it's not possible to enter in too many details, but especially for the second part, the second lesson, I will enter a little bit more in details, since I heard from you that maybe this can be interesting, about the VOF and level set method. So I will focus on this more on this part, let's say, on this and second part, let's say. The first one will be something that we are going to speak about, even simulation for gas-solid flows, for example. No, they are completely different because you don't have an interface and so on. So, okay, but something general, but I think that is interesting. Now, today we are going to speak about heat pipe. This was 5.3. And I'm going to speak about the fundamentals, the applications, and in fact the last part, again, this is my style as usual, and I will speak about, let's say, heat pipe fundamental. The last part, in fact, is about the supplementary material, because we don't have time to enter in this, but I will give you this part because I think that it's interesting to know the different applications that we may have with the heat pipe. Only to tell you something about my experience in heat pipes, I started with this topic in 2007. Yes, 2007. So about 18 years ago. And the idea was to have, let's say, to try, let's say, to simulate the behavior of a satellite thermal management system. So my interest was really on satellites because I did some project for the Italian Space Agency, mainly based from, let's say, on the concept of having a pumping system. So was something, the idea was, is it possible to bring in space a pump to have a flow boiling? You heard now, no? This was the idea because I came from microfluidics. So I work in microchannel cooling, so this was the first idea. And I got a couple of projects. But then at that point, 2007, I said, why not trying to understand if it's possible to have something flexible? So my adventure in heat pipes, so let's say now 18 years, started with the idea that we may have something for deployable system in space. But before going so far, I started studying, let's say, the heat pipe, the usual heat pipe, sintered heat pipe, and so on. And at the same time, I invited one postdoc from Belarus. He came to me and he said, but do you know something about pulsating heat pipe? Well, yes, I know, but I mean, nobody is doing some research on this topic. I don't know, it was 2007. There were some work in 2002 from Samir Kandekar, who, by the way, passed away, a professor in Kanpur, at the IIT Kanpur, passed away, let's say, in December 2023, but nothing else. And we started with the pulsating pipe. In fact, I'm studying pulsating pipe since 18 years. But together with this, I'm also working with the sintered heat pipes, looped pipe. There is someone in this room working with, and from Guwahati, from IIT Guwahati. And let's say thermosiphon. I work with sodium thermosiphon, so high temperature thermosiphon, and many other things. So these 18 years of, let's say, career in heat pipes are really, let's say, a very nice extended adventure in the topic. So there are, let's say, two categories of heat pipes. One is the wick heat pipes, and the other one is a wickless heat pipe. The wick heat pipe, as the name is saying, they contain a wick. So the principle is that in order to bring, I believe that everybody knows, because already Arvin said something about heat pipes, so I don't need to repeat. But the principle is that the liquid is going from the condenser to evaporator because we have something like a capillary suction, okay? So in order to have the capillary suction, we are using a sponge, and the sponge is a wick, okay? So we can have, say, the classical wick heat pipe, no? We have in our computer, even in our phone, we have this such systems, and in many other applications, in space, of course. And we have looped pipe that are another kind of heat pipe. We are going to see that, where we have, let's say, that the evaporator and the condenser are detached, while in the first system they are together in unique system, unique tube, okay? And then we have capillary pump, looped pipe, so we have various forms, okay? In fact, I belong to the International Committee for Heat Pipes, and sometimes we are meeting each other, so we have these meetings, and we are saying we should have something like a standard terminology, because every time that we are going to the conferences, we find other name and so on. So it's a little bit complex here. So now I'm referring to the usual standard textbook on heat pipe, okay, as for the, let's say, these kind of names, the definition. Then we have a wickless heat pipe. So as the name is saying, here we don't have a wick. So we need to rely on other system or other processes to bring the liquid to the evaporator. In a thermosiphon, we are bringing the liquid back to the evaporator because we are using gravity, okay? The hybrid looped thermosiphon is a system that we are using the gravity still, but we have the chance to have maybe capillaries, so it's a kind of mixture, hybrid system. Because on the other side, on the other end, we have the pulsating pipe, where in fact we are using the, capillary, the capillarity of the tube in order to push the liquid slug toward the evaporator, because we have an expansion and the contraction of the vapor inside. So in fact, there is a kind of thermal pumping in a PHP. And this is possible only when we have a capillary system, because it's the only way that a liquid slug is completely filling the tube. So it's something like really, a cork in a bottle. So and then if we have an expansion of the vapor, then it's going to move the entire liquid. If it's a stratified flow, of course not, because the vapor will pass over, and then it's not working anymore. Okay? So these are, let's say, the system we are thinking. So again, this is the classical representation. It's very famous picture that you can find in internet. I'm using always that, but it's interesting because you can really see that we have an evaporator, we have a tube that contains a wick, and because of this, the liquid that is formed in the condenser is going back, as I said. And there is a so-called adiabatic section. Of course, the definition of an adiabatic section in this system, like for the pulsating pipe, is a little bit, let's say, blurred, in the sense that what is the adiabatic section? We have, for example, a copper tube is not really that here we are going to insulate. For the looped pipe, is a little bit better because the evaporator and condenser are detached. So in fact, the vapor line and the condenser line can be even really adiabatic, can be insulated. Okay. For this system, okay, we have an adiabatic section in the sense that maybe we are going to cool only one part and we are going to heat one part of the tube. Which are the advantages of the heat pipes? Well, I think that Arvin already said something, so I'm going fast. The high thermal conductivity is, of course, one very important point. So we have an equivalent thermal conductivity that can be very, very high. So even 90 times, 100 times the copper. So in fact, it's something like having a tube that has a very high thermal conductivity, so a kind of highway for the heat. With another big advantage, because since the tube is not full, it's not solid, because we have the space for the fluid, the kilowatt or the watt per kilogram of the device is very high, because the weight is much less than a solid bar, okay, a rod. Okay, so in this sense, it's quite useful for many applications where the weight may be important, even in the laptop, honestly. Okay, but of course, for space, it's really very important. Another point that is good for in using the heat pipe is that we may have a variation of the power in the evaporator, switch on and off. Okay, but then the condenser may remain at a similar temperature because we have a thermal inertia and we have a phase change. And as you know, I mean, with in the phase change, we can absorb or release heat for a given pressure plus minus at a constant temperature. Of course, here is an isovolumic system. It's not isobaric, okay? But in any case, we may have let's say, the thermal inertia and the latent heat that are, let's say, allowing us to have a variation of the power at the evaporator without big variation or the same variations at the condenser. Okay, and pay attention that, of course, I think Arvin said that. I couldn't see the lecture, but his lectures. But the heat transfer coefficient at the evaporator are different with respect to the heat transfer coefficient at the condenser, usually are higher. Okay, so this means that if you want to balance, because of course the energy that is going in should be equal to the energy that is going out. So in this sense, the area of the condenser is bigger than the area of the evaporator, otherwise there is no balance, let's say. Okay, HA of the evaporator must be equal to the HA at the condenser. And then we have also the chance that even if the heat is very concentrated, so we have hot spots and so on, the heat is distributed first on the wall, on the case, and then it's going into the liquid. So in this sense, even if we have concentrated heat, it's fine, because we may have a hot spot and a dry spot. What is a dry spot inside a pulsating pipe or, let's say, a looped pipe and so on? It's a place where we don't have liquid anymore, and it's not possible for the incoming liquid to, let's say, to the incoming vapor to become to phase change, so to become liquid again, because the temperature is too high, for example. So we have a lightning frost phenomena and so on. So in this case, we have a problem. Well, but even if we have a local hotspot, the system is still working. This is the reason why we have, because it's going to use the case to transfer the heat. Of course, it's a very extended hot spot, and the dry spot doesn't work anymore, of course. In fact, we are going to see the limits. There are limits, okay? So I said already the things about the evaporator. So, and then another point that is very interesting for the heat pipes, that we have really a lot of possible geometries, no? If I build a kind of photo book of the possible heat pipe, and you can Google, and then you can find really a lot of different species, different forms, different geometry, heat exchangers based on the flat heat pipe, and so on and so on. So there are really a lot, okay? And also interesting, for example, the system like a looped, this is a looped pipe. The looped pipe is interesting because we can have transfer of heat at long distances. Even 6 meters and even more. So we have the evaporator that is 6 meters distant with respect to the condenser. So another point that is very interesting for the heat pipes is that we may have heat pipes from cryogenics, so liquid gas, up to metal liquids, so liquid metals. So we can have minus 200 degrees, minus 250 degrees. Of course, there is a problem in the case, more than the fluid in this case. So we must use cryogenics techniques. And also maybe we can have even lithium heat pipe that are going up to 1,500 C or even higher. Myself, I use, for example, sodium in a thermosiphon with 1,000 degrees plus minus at the evaporator. As you can see already here, for the different fluid, we have, and here is the power that can be absorbed by the very similar system, okay? The power is reaching a maximum. So one of the problems of the heat pipe is that the people in the companies, for example, they use a heat pipe like, okay, we have something that is something like a rod, a copper rod. So you put the rod, you know the thermal conductivity, you're doing your finite element analysis, and you get an answer, it's fine. Well, it's not like that. First of all, because the thermal resistance of the system is depending on the heat flux and the power. It's not anymore something constant. So K is a function of flux, is a function of power in this case. The equivalent K, the equivalent thermal conductivity. And another point is that we are going to see there are limits and there is an optimum in using the heat pipe. It's not possible that the heat pipe is working with all the powers are in the same way. We have heat pipes with also a lot of different dimensions. We cannot have heat pipe very, very small because we are going to see there is a pressure drop inside. So if the channel inside is too small, and it's very difficult to get something. Even if, for example, a group, I think in Korea, they did recently a pulsating pipe where in a let's say a flat plate pulsating pipe in a thickness of 0.4 millimeters. 0.4 millimeters, okay? Pretty. But of course what happened, so it's possible, but the efficiency is low because again, the system is really very, very thin. We can have really various kinds of heat pipes. I'm not entering now in the details. So, let's speak about the limitations of heat pipes. As I already said something about the dry out. So, we have a capillary limit. The capillary limit means that the capillary pressure is too low to provide the liquid to the evaporator. Okay, so in this case we are going to have dry out at the evaporator. If it's only one spot because we are going to, let's say, to heat the evaporator in only one position is something. But if the capillary pressure is not enough to bring the liquid to the other side, then of course it's a big problem because it's a general dry out. It's not only one point. Another point is the boiling limit. Again, this is when the heat flux is too high, and inside we're going to have, for example, a phenomenon like Leidenfrost and so on. So again, it's not possible for the liquid to arrive until the end of the evaporator. Then we have the entrainment limit. The entrainment limit is when the vapor is going inside and is pushed, of course, from the evaporator to the condenser, and there is a liquid that is trying to go from the condenser on the other side, and this velocity of the vapor is so high that it's going to strip, it's going to break up the interface, or it's going inside the wick, when we have a wick system. So in this case, the liquid is not able to arrive on the other side, yes. Sonic limit, well, in some case, we have that the vapor velocity is really very high, and then we have a choke flow. Again, the choke flow is preventing the liquid to come back. And finally, we have the viscous limit. For example, when we have, let's say, a liquid that was with too high viscosity, for the design that we have, or for example, we are going very low with the temperature, the viscosity is going to grow, and then we may have a problem. So let's study a little bit more what is happening in terms of limitation of the heat pipe. So here is a classical image from Peterson 1994. Nothing changed from 1994, so I can use this image. We have, this is the temperature, this is the power, and when the temperature is very low, for example, we have the viscous limit, we may have the sonic limit. Also at this point, we have the capillary limit, the entrainment, and the boiling limit when the temperature is too high. The wick design. Well, we may have a lot of different kind of wick design. We may have arterial. This is an arterial heat pipe. So we are using this capillary as, let's say, our capillary to bring back the liquid to the evaporator. We may have groove heat pipe. We may have different kind of wicks and so on. Here, really, if you're coming to the conference, heat pipe conferences, you have really a big list now of possible options and so on. Everybody's studying, for example, maybe gradient of the wick, two kind of different porosity, biporous systems, and so on and so on. So there is a very, very extended literature on this topic. Let's think about the capillary limit. So we said that it's happening when the capillary pressure is not enough to bring back the liquid to the evaporator. So this means that the capillary pressure should be equal or bigger than a sum of the pressures drops, or let's say the pressure that we need to win in order to bring the liquid to the evaporator. And for example, this means that delta Pc, the maximum value, must be bigger than delta P tot. So we may have these terms, delta PV, delta PL, delta PB, and delta PH, okay? And let's understand what these values are meaning. So this is the classical behavior of the pressure inside a very standard PHP with a wick, okay? So in the evaporator, we are creating the capillary difference linked to the fact that we have the wick, okay? The wick means, let's say that we have a pressure that is linked to the pore size. You know that the pressure is linked to the Laplace pressure, and the Laplace pressure, let me write that. The Laplace pressure is something related to the dimension. Sigma r, sigma divided by 2r. So, but this is the idea. So, this is linked to the surface tension that we may have. Okay? So, and of course, due to the fact that we are, let's say, we have a flow, we are going to have different pressure drops. Okay? So, for example, if you are thinking to delta PL, what is delta PL? Well, is the pressure drop linked to the fact that the liquid must pass into the porous media, into the wick. And so the value of delta PL over the X is equal to minus the viscosity of the liquid multiplied by the mass flow rate of the liquid inside the system divided by K, AW, and rho L. AW is the area, the open area of the wick, okay? And K is the so-called permeability, okay? Is a value that is related to the pore size, the pore volume, in fact, and can be used. It's a little bit rough, but it's okay. There are many other, let's say, ways to write this value, but is very clear that is depending on the dimension of the pore, and then there is a factor FL that in fact is a kind of tuning factor, and then the Reynolds of the liquid. What is important to say in a wick, you may have very small pores, but the heat pipe is not working. Why? Because one can say if the pores are very, very small, because the capillary pressure is going to sigma divided by r, of course the capillary pressure is going up, no? With the 1 over r, so it's going very fast. So, well, yes, it's like that, but we need that the wick is also topologically open. Because you can have very small pores, but if in some point the pores are very small, but they are blocking the passage, doesn't work anymore. So you create a lot of pressure, but local, and there is no chance to have a flow. So you need to build a system that is very good in terms of capillary pressure, so with small pores, but pay attention that must be open, so the liquid must pass. And this is the wick permeability, okay? So the wick permeability then is not only a question of epsilon, V pore over V dot, for example, but is really linked to the fact that we must be sure that there is a connection between one pore and the other, otherwise it doesn't work. So-called wickability. Okay. Another point is that the PV, delta PV, what is? Is the pressure drops linked to the vapor. And here the things are, let's say, easier in the sense that it's a classical flow. Of course, if we are not going to the limit of the sonic limit, no, with the compressibility effects, we can say that the flow inside the laminar is laminar, both for the liquid and for the gas. So we should be always in situation like these ones, okay. And here what we have is that there's a classical part linked to the pressure drops, but then also what we have is the fact that there is a pressure due to the phase change. And now you should remember what I said in my talk about, my lecture about the equations for the two-phase modeling, so the multi-phase flows, that there is a pressure, so there is a work linked to what? The mass interaction term. You remember? Wi. The theory that I described is super important because it contains all the information that you're going to use. Of course, it was very concentrated, but I mean, this term is very important because we are going to find this term also tomorrow when we are doing CFD modeling and so on. We are going to find the same theory translated, okay, for the different cases, but we are going to use the concept. The general concept I gave are really the basic part. So, how much is the K? As you can see here, there are different expressions for the grooves, an artery, an annular wick, a screen wick, and a packet sphere, and so on and so on. So, these equations are mainly empirical. So, here is 122 and 137.5. But what we are doing when we are doing simulation of heat pipes, in fact, is that at least for the first time we need to tune, because these values are important and because they are really deciding the permeability, so they are deciding the value of delta PL, so we need to tune them. One can think, why can we, let's say, simulate a heat pipe with using CFD? Because this is a good question, of course, yes. Well, it's possible, yes, but again, we don't know exactly the structure of the porosity. What I did, for example, once I studied the droplet impact onto porous system, and we had a stone that was porous. We went to let's say, a system that is with X-ray. We had the structure, the internal structure. From the internal structure that we studied with the X-ray, we have a CAD design, so we knew the structure of the system, and then we did the simulation. But imagine to do something like that for all the heat pipes. It's super long. So in principle, it's possible. I can say, okay, it's not, but is it worth or not? I mean, this is the point. Of course, we need to have a conservation of mass inside, so otherwise we have a problem. In the sense that, of course, the power that is going in the evaporator must be equal to the power of the condenser. Of course, this is happening at the steady state. In fact, we are always speaking about a startup power or startup temperature in order to activate the heat pipe. So this is happening in a steady state condition. But when you switch on, there is a ramp up of the temperature. So this means that even if the heat pipe, a simple heat pipe, is very fast, I I did a mistake, I must say, because I wanted to bring one, and I forgot. I forgot at home the one heat pipe. So because it's very interesting to do experiments, even on the table, with a piece of rod, a simple rod, and a heat pipe, and you will see that it's very fast. It's really active, but it's not always the case. For example, for pulsating heat pipe, for space application, we have a problem of startup. And sometimes also for looped pipe and so on. For example, this is a point that we need to study in order to be sure that the system is working. Another point is that if we know the mass flow rate along the heat pipe, we can define an effective length of the heat pipe. And this is also another point that is pretty important, because we can assume that the effective length is 1/2. This is an estimation, but is okay. 1/2 of the evaporator length plus the length of the so-called adiabatic. This means that where we don't have the evaporation, we don't have the heater, and we don't have the cooling system, let's say, plus 1/2 of the condenser length. So the total, we can write using the effective length, we can write the delta PL, for example, also the delta PV. So in this case, we have an estimation. We are going back to this point. Whoa, my God, it's very late. Okay. Boiling limit, I need to accelerate, is linked to the power, okay? And of course, it's linked to the boiling that is happening inside. We are boiling. This is, imagine, if a wick system is a boiling porous media. It's a boiling in porous media because we have a liquid that is going inside the porosity. So this is a very, very difficult, complex phenomenon, because you have also the local pressure is not the pressure that you have when the liquid is in the bulk, because you have pores. So you have a difference in pressure due to the capillary. Okay? Pressure. So this means that if we have a given pressure, then inside the different pores we have a different pressure, so we have a different saturation temperatures. Right? So, and then you start thinking, well, this is not easy then. Because, and then it depends also on the wick. If the wick is conductive or not. Imagine so to have one pore like that and big pore like that. Big means 10 microns, 5 microns, something like that, no? But you have difference, and so the two temperatures are different, because the saturation temperature is different, because the pressure is different, okay? Then, of course, if the conduction is very strong, then you have really a very high efficient mechanism of transmission, because then you are going to homogenize the situation. So, for example, then it's very important, a steel wick, the wick made by of steel is not efficient as a wick made by aluminum or by copper and so on. So this is also another point to think about. But what is happening is that, of course, the boiling is linked to the fact that we have nucleation inside, okay? And the nucleation is a very complex phenomenon. It's not, there are, let's say, expressions for the nucleation, but it's quite complex. Another point that you saw, I think, with Arvind is that when we are dealing with boiling, we are dealing with a boiling onset temperature. So this means the first temperature where we are going to start to have bubbles inside. And the bubbles also in the capillary system move in a very complex way. And the critical point, the critical superheat. So this is another point to study, okay? When the heat flux is beyond a given value that is determined by the fact that we have reached a given temperature, okay, we may have the boiling limit. The point is that how much is the thermal conductivity of the system? Because every time that we're speaking about boiling, we're speaking about the thermal conductivity of the liquid, in this case, plus the porous wick, if we have a porous wick. And there are many possible equations, Again, these are, let's say, empirical equations. So there are averages that are used to determine what is possible to have. For example, this is a work that I have done some years ago in 2013, and this is a lumped parameter model of a sintered heat pipe, okay, where we describe the sintered pipes with the lumped parameter network, okay, was good. So it's possible to write the equations for the network. This is not the only way, but it's our way. I have the code, which is interesting because also is a code with a thermal capacity. This means that is a transient code. So we can see the ramp up. We can see the situation when we have a heating that is growing or a condenser. For example, when we are in a satellite, on the condenser side, on the radiator, we have, of course, a varying condition because we have the orbit, that is changing every time the condition. So we can simulate what is happening in a heat pipe. So I'm not going for the equation, but you can read this paper if you want, because otherwise there is no time. But there are, let's say, the equations that you saw before that are implemented all together in the code. Another point, and indeed, when we did this, in order to get some of the parameters, we try to optimize the code with experiments, because some of the parameters are, as I said, fitting parameters, so you don't know exactly. We are lucky enough to say that some of the unknowns are not so determinant, so they are not so heavy in terms of the effect on the final result. But one needs to pay attention. Then we have a capillary pump looped pipe. Let's say this is an interesting system, okay? That is, we have a kind of, let's say, reservoir, okay, of the liquid, and you can see the structure of this system is indeed very similar to the looped pipe, okay. What is important in this system is that we have vapor line and liquid line, like for the looped pipe, and they can be very long. Now we can have 5 or 6 meter long system, okay, and so a capillary pump looped pipe, which is extremely efficient, is a looped pipe. A looped pipe is really very efficient, and also in this case, we wrote a lumped parameter network code in order to simulate a looped pipe. So again, in this case, we are going to have, let's say, what is important let's say in a looped pipe. What is happening here? Here we have an evaporator, where we have the wick. So the evaporator with the wick is building up the capillary pressure, okay? So what is happening here is that the vapor that is formed is going to push, as a high pressure, that is going to push other vapor here in this line, is arriving in the condenser, and here we have the formation of the liquid, okay? And the liquid is pushed in the other direction until a compensation chamber, okay? And you can see from this graph that the compensation chamber, we plotted the compensation chamber at a given distance from the evaporator with the bayonet, but in fact can be together, can be in the same piece. We may have a room, a space for the liquid to enter. And this is avoiding the dry out, because if you have the liquid that is going inside, there is a kind of reservoir for the liquid. Otherwise, we may have a problem, because the critical point is that we need to be sure that the liquid is going back, is pushed in this direction, okay? One way is to have, for example, the liquid line that is small, but then we are reducing the length, the distances, because if we have capillary, we have more pressure drops. But of course, it's more efficient, because we are pushing the liquid from the condenser to the evaporator. But if we would like to have something bigger, so at the end here we have a two-phase system, because we have a liquid, but then the vapor is going inside, so it's creating an extra pressure, and slowly, we need to be sure that here we have completely condensed everything, which is not obvious at all for the different condition of usage. But then, okay, if you have completely done this, we have an extra pressure here that is bringing back the liquid. Well, we need to be sure that the mass flow rate of the liquid is enough for the power. So this is the reason why we have the compensation chamber. One of the problems that we have is that since the compensation chamber is here and we are forming the vapor, we must be sure that the vapor is not going in the other direction. Okay? And there is another point that we have the heat. If the compensation chamber is attached to the evaporator, we have a heat leak from the evaporator to the compensation chamber. So we are losing some power to the compensation chamber. For the pulsating heat pipe, the pulsating heat pipe is a system where, as I already said, we are going to fill the system. For all the system, I didn't say that. I need to remember. I think that you know, but it's better to say that we are not filling, of course, we are not filling completely a heat pipe with a liquid. We have always a fraction of the volume inside that has the liquid at the beginning, okay? So-called filling ratio. The filling ratio is quite important because if you are changing the filling ratio, you may have different performances. So, okay. So, in the case also of a pulsating pipe, we have, let's say, 50% filling ratio, for example, and from the very beginning, we have a chaotic situation, and the system is a random, completely random, where we have some vapor and some liquid. Of course, why? But it's very clear, is the quality. The vapor quality at the very beginning is not 0, it's not 1, but it's very small, but still, no? So we are going to have vapor inside, okay? So it can be 0.05, something like that. But we have a vapor quality, so we have two-phase system. So what is happening, if the system is capillary, there is a movement of the liquid slug due to the expansion of the vapor, okay? So what is happening is that inside the system, we are going to observe something like that. This is a visualization of what is happening. So these are, let's say, bullets, these bullets here, so they are vapor bubbles, okay, that are moving inside. And what is happening? Since the tube is not a tube, an infinite tube, so the liquid slug, are going to the evaporator, producing the vapor, and so on. The vapor is going to expand, but it's closed. The system is completely closed. No, it's a closed end. So what does it mean? That of course we can say, then it's moving. Yes, but it's moving. This means that there is a reaction on the other side. Okay. In fact, one of the methods to study a pulsating pipe is a kind of mass spring system, because it's something like an oscillator. Something that is happening in one point is going to produce a reaction in another point. Okay? So, in this case, why is pulsating in pipe? Because in fact we have a pulsation. We may have in fact pulsation, and we can have a circulation inside. So, why is it interesting? No need for external pumping work, simple construction, low manufacturing, less size and weight due to the lower mass, and high heat fluxes. Of course, with respect to a sintered heat pipe or a loop heat pipe, the first point is the same. Simple construction, no, it's simpler, a pulsating heat pipe. So it's like, because we are doing loop heat pipe, and it's quite complex to have a loop heat pipe that is running, because it's not obvious to design the evaporator. Something can be a problem. So the pulsating pipe in this sense is very simple. The manufacturing costs are lower. It's a tube, okay? Since we don't have a wick, the kilowatt or the watt per kilogram is even higher, because we don't have the weight of the wick. We can approach high heat fluxes, but not so high as for the sintered heat pipe, honestly, okay? So the heat fluxes are lower. Also lower with respect to the loop heat pipe, okay, in a pulsating pipe. However, since it's simple, we can cover a wider area, so we can absorb also a lot of power. But we cannot, let's say, if we have something with very high heat fluxes, it's not for the pulsating pipe. You need to go let's say, with the looped pipe or with the heat pipe, or other system on ground, thermosiphon and so on. Okay? And it's possible to work without gravity. This is my work, the work of my group. We were, let's say, the first, I think, to have an experiment on a parabolic flight that was able to prove that the system was working. Okay? Of course, with the less efficiency, but still possible. Then, how to model a PHP? So, in principle, here we have a vapor plug, a liquid slug, and a vapor plug. Okay? The vapor plug, the bubbles, they have around a liquid film. And there is a lot of, say, effects due to the liquid film dynamics. Because if you think the vapor plug is moving and the liquid film is going, it's something like a coating. Imagine the contrary. Don't look at the vapor, look at the liquid, okay? And if you move a surface, let's say with respect to another, it's a kind of coating, no? Because you are coating the system. The liquid is staying there, and you are coating the plate or the tube, whatever, okay? So the liquid film dynamics is very important, okay? So just now, I think that the one PhD student from China, she's going to work in my group because we would like to implement the film dynamic inside this model. At the moment, our model is that we have a given thickness, and the thickness is related to the velocity of the vapor plug. So the vapor plug is going in this direction, and we can change the, let's say, the thickness due to the velocity, because the thickness of the liquid film is related to the so-called capillary number. The capillary number is mu divided, okay, mu, divided by sigma, okay? Viscosity multiplied by the velocity divided by the surface tension. So there is an equation that is saying how much in a coating, for the coating, how much is the liquid film thickness due in a function of the capillary number. But we are not introducing really dynamic. So the dynamic of the film can be, for example, with waves. We can have a breakup and so on. This is not included, okay, yet. We are thinking to do that. But let's say we have this kind of system. And we are going to consider the control volumes here. And we have control volumes for the liquid slug and the vapor plug. And we are following with the Lagrangian, we can follow the liquid slug and vapor plugs in the tube. We need to solve the momentum equation. We need, of course, to have the mass conservation equation and so on and so on. And the energy equation, sorry, of course. Another point is that we are assuming the radial heat transfer. We can also think to the axial heat transfer. It's not really a big problem to implement this one, but the radial heat transfer is very important. Okay. So, there was a model. The first model, I think, of PHP was from Holle and Fagri in 2005, I think. Was one very, very, let's say, early work, pioneered work on this field. There were many problems with this, but still they tried to do this work. Something happened with the presentation from from my computer to this one. I don't know, but I'm going to speak on this and so on. So, other simplification that is possible to do. I'm saying that because I think that is important to you to understand. I could have put the one of sintered pipe. I decided to do this one for the pulsating pipe because I know that in this audience we have 2-3 of you that are working with pulsating, so maybe there is more interest in that in a classical sintered pipe. So, numerical model. So, we don't have, let's say, our code is in our code, the density of the vapor, the density of the liquid is constant, okay, and viscosity is constant. the density of the gas is changing, okay? We have two versions. One is with the ideal gas, and the other one is with the real gas. But in principle, we have a variation of the density due to the temperature, okay? This means that the thermophysical properties are evaluated as a function of temperature. However, in the momentum equation, we are not considering derivatives. So we are not considering the derivative like in a compressible flow. Now, yesterday we saw that. So if the rho is included or not inside the derivatives. No, for us not. It's outside the derivatives, like for the incompressible flow. However, rho depends on T. So it depends on the temperature that is coming from the energy equation. Okay? But it's still incompressible. The advection term is neglected. Yes, I mean, is a way, but it's not, for example, it's not the viscosity is there. So we have a viscous dissipation inside. So this is also important. Okay. And the other point that is very important is that we have a zero contact angle at the wall. So the liquid film is always present. So we don't have the situation where we have a dry spot. So we have in contact, the vapor in contact with the wall. The liquid film is always present all over the PHP. Honestly, since many years of work, we have seen a lot of cases and so on. This is happening in most of the cases if you are not going to the limit. So if you are staying, let's say, in the limit of working of the PHP, we have liquid film everywhere. Of course, if you have a little bit too much flux, for example, then of course you are creating a dry spot. In the case of dry spot, the contact angle is becoming very important because it's deciding the form of the meniscus. Okay? So in this case, we don't have zero contact angle. Inside in the vapor plug, the pressure is uniform. Okay? And in this first version, as I said, there is ideal gas. Okay? The enthalpy is considered a saturated condition. And then we got a big problem. We work a lot on that. Because, of course, what we may have is that the bubbles can break, can coalesce. So we need some mechanism, some closure equation to understand how it's possible to determine when the bubble is going to split or the bubble is going to merge. Two bubbles are going to merge. Because the liquid film, the liquid slug is becoming very thin. So, and of course you can understand already that there is the threshold, and the threshold is somehow empirical, so it's a kind of fitting parameter. Another point is that, no, it's like something like that. Of course, the other point is that we need to rely on heat transfer coefficient, like Arvind was speaking about heat transfer coefficient for evaporation, boiling, condensation. No? In this case, the heat transfer coefficient that we're using with Nusselt, function of Reynolds and Brandt, in fact, are usually working for a flow with a given velocity, maybe with an entrance length, is not a problem, but the acceleration is not there. So this can be, of course, a big problem, because in a pulsating pipe, there is an acceleration of the vapor plugs and liquid slug. Okay, so this is again a simplification. Okay, so and this is very interesting because try to go to Google Scholar and find a paper dealing with the heat transfer coefficients with accelerating or decelerating flows. Try in two-phase system. There is really so very few works on that. This is really a kind of research that you could do because it's very interesting. Okay, experimentally there is nothing. It's very difficult to find data. So, okay, you need to rely to something. So, the time is passing very fast. So, you are going to see in the slides, but we are going to build a model with, say, a classical equation for momentum. This is for example, for the liquid slug. And so we have the terms like the gravity, the vapor plug, expansion and compression, the viscous shear, and the local pressure losses. So this is another point. In the pulsating pipe, what is also important that we have turns, no? So then we need to add always the pressure drops linked to the turns. If you are not considering the fact that you have these pressure drops, very classical, very classical estimation of the pressure drops when you have liquid or gas passing on, in an elbow, 90-degree elbow, for example, you have a concentrated pressure drop, no? Instead of only a distributed. But the concentrated pressure drop is very important because we have a lot of turns. So this is not negligible. We need to consider that, especially because sometimes you saw from the images, from the videos, the velocity of the vapor and the plugs is not so small. We are speaking about 1-2 meters per second, which is not, in a small device, is very fast. 1-2 meters per second, depends on the conditions. As I said, we have a liquid film thickness, and so then this means that we can calculate the heat transfer, and we can use classical equations. I hope that in the PDF it's not like that, but in my screen worked, so I think that the PDF should be okay. If you have any problem, let me know, so I will arrange, but I think that it's something really related to the fact that I passed the the PowerPoint from one computer to the other. But okay. Yes. The HL, for example, we use a classical equation, Shah and London. As you know, when we are dealing with this kind of system, with the phase change, the accuracy of the H is quite limited. So we are speaking always of plus minus 30%. We need to survive with that. It's not possible to change this. And then so we have the different condition, Coolebrook for when the Reynolds is below 10,000. Usually we are in the, let's say, also in laminar conditions. Because the tube is so small that even if you have 1 meter per second, we are with a Reynolds that is low. But we implemented everything. And then of course also for the boiling, we use an expression for the boiling in order to have the heat transfer coefficient for the boiling, and there are tens of possible empirical, semi-empirical correlations, and we use the one from Gunger and Winterton. But again, you can use other things. In fact, we tried with other, let's say, this is very interesting. Since one can say, okay, but this is maybe not working and so on. Look, the heat transfer coefficient on the boiling side and the condenser side, in any case, are very, very high with respect to the rest. So maybe it's not 10,000 watt meter square Kelvin. Maybe it's 15,000 or 20,000 watt meter square Kelvin. We tried, doesn't change anything. So the effect of having something there of a factor 2 or 3 at the end is not changing because the value is already very high. So the difference of temperature between the wall and, for example, the vapor plug or the liquid slug is very small. The fact that it's much more important the liquid film thickness because the conductivity of the liquid is small. But the heat transfer, 10,000 or 50,000, 20,000, at the end is the same. There is no effect. Of course, we have these equations for the boiling and for the condensation. The point is that all these equations, they contain the vapor mass quality. So M of the vapor divided by the total mass. And this is, of course, a problem because we need to estimate the value every time. And of course, it's going to be a local value because the quality, there is a local value for this quality and not the overall quality of the system. But again, this is introducing something that we are not sure so much. But we can also think that, okay, Another estimation is to use, let's say, the local, no, sorry, not another. The estimation is to use the local one, and so you can see that we created the formula saying how much is the local mass quality for the vapor plugs. And how to choose the liquid film at the end, now we know that the liquid film is about 50 microns in most of the cases, 50, 100 microns, something like that. The main problem that is not here is the dynamic of the liquid film. This must be included because this has an effect. And this is the reason why with a PhD student from China, I hope to implement this because Dr. Nikolaev, that has maybe the best code in the world for PHP, that is the Casco code, okay? He implemented already the liquid film thickness and with the right dynamics, so with the waves and so on. He wrote a very nice paper in Journal of Fluid Mechanics about that. And in fact, he observed that without considering the liquid film dynamics, you are going to be inaccurate, okay? So this means that my code at the moment is not as good as the one of Nikolaev. There are other codes, but there are not so many. I could count in 4 or 5 codes, not more than that. Finally, I don't have time, but of course, only to say that the code was validated, okay? With different kind of PHP, with a tubular PHP, flat plate. No, only tubular PHP. Only tubular PHP. The flat plate, we need still to check this one and so on. We did visualization and so on and so on. So this is now here the part that I told you. That's about the supplementary material. I'm 2 minutes late now. Sorry, but I think that was interesting to go through the model, no? Of course, if you're interested in this model, I'm very happy to, let's say, to help you. And even if you're interested really in using this code for pulsating a pipe, I can give you the code, okay? Of course, maybe if then if we can publish something together, I'm very happy, let's say, but I can handle to you. At the moment, the main issue is that some part of the code has comments only in Italian, but now with the ChatGPT should be okay. So you can translate from Italian to Hindi or Tamil or English and so on. So, okay, I think that we finished with the heat pipes. I'm staying here until 1 is again for your questions and what you would like to ask, and then see you tomorrow. Okay, we are going to do interfacial phenomena, so surface tension, and we are going to speak about how to simulate CFD simulations, spending a little bit more time on liquid gas systems, a little bit more, okay? Because I saw that from, let's say, from that nobody's working really with gas solid, right? Right? You are the only one. Sorry. I have a part, but only a few slides, because I cannot cover everything, okay? But I have one part for you. For the rest will be liquid gas, VOF and level set and so on. So DPM, you're using DPM? Eulerian. So I will speak about Eulerian, and we'll speak about Eulerian with parcels. Maybe you're using parcels. No. Okay. Then is also two fluid. It's a 2-fluid model. Okay, I'm going to speak a little bit about 2-fluid model. Okay, 1 slide, but it's okay. Okay, thank you so much, and you can stay and you can ask questions. Otherwise, see you tomorrow.